And it's my great pleasure to introduce the speaker today, Denis Getskori from Harvard and the HOS, who will speak on the Tamagawa number formula of a function field.
Thank you very much. It's great fun to be all over. Indeed, so it's Tamagawa number formula over function fields. It's a joint work with Jacob Lurie. So I'll present a somewhat simplified context. So we fix a curve x, it's a smooth complete curve over function fields, over a finite field. And we fix g to be, g would be semi-simple and simply connected group. Semi-simple. And to simplify, I'll fix it to be over the ground field. So more generally, this story works for group schemes over, actually for groups over the field of rational functions on the curve. Okay, so I'll present the formula in the way in which, well, in geometric terms. It's not the classical way in which one presents the Tamagawa number formula. So we consider bun G, it's the moduli space, moduli step of principal G bundles on the curve. So this is an algebraic stack over a Q. It's not quasi-compact. So yet, so if you have a quasi-compact stack Y over a Q, you can try, well, you can calculate the number of its points over a Q, but points must be taken in multiplicities. So by definition, if Y is quasi-compact stack, this is the sum over Y, which runs over the set of isomorphism class of points, and for each isomorphism class you assign a weight. So you take 1 over, you take in the group of automorphisms of this point, and you count the number of points of this group over the finite field, so you sum this thing. And it's a finite sum if your stack is quasi-compact. Now this guy is not quasi-compact, so the sum will be infinite, and one runs into a convergence problem. But it's a classical fact that this thing converges if the group is semi-simple. So our interest is, we are counting bundles. Okay, and now I'll state the Tamagawa number formula in this case.
So you said this holds for quasi-compact stack, but now this holds more generally now? Is that what you're saying?
There's nothing to hold. This is the definition.
But it converges, even for
it converges for this particular one.
Okay. Wasn't this a work of Kai Barron in which he had some...
Kai Barron, yeah.
Yeah. He worked it out. I mean, but this convergence is a very classical fact. It's the finite volume of the automorphic space. That's what it is.
Who worked out?
Kai Barron. He had a way to use formal power series and convergence.
But you have some implicitly you have the fact that every bundle of the type considered is rationally trivial, is it true?
For simply connected, yes.
And this is somehow used to relate what you're doing to the classical form,
Yes.
But now, when you were working with this more general situation of groups over the function field, the simply connected, then it is not necessary, is it?
It is.
What is true?
So, well, I don't want to call it a set. Well, it's okay.
So when G is defined only over an open, then you have to extend it to the whole, because...
Yeah, so, okay, in that case, what you do, you kind of, to state this thing, you first extend your group over the fraction field to a group scheme over the entire curve, and then you state it. So the way I'm going to state it is specifically after the loop has been extended, and that's why I made the simplification, because I don't want to go to that discussion.
And is it still true in that more general case that the bundles are rationally trivial?
Pardon me?
The fact that principal bundles on X are rationally trivial,
Yes.
is it true in the more general context?
Yes, simply connected is true.
Ah.
But let me just stick to this case because it's much simpler.
You have
To jest huk, ja.
Oh,
Huk, no.
c'est derrière. Tu baisses le numéro 2,
Ah, du numéro.
don't put white. Ne laisse pas de blanc parce que ça dérange la caméra.
Donc,
Tu baisses le blanc.
je baisse le.
Ouais, c'est...
Ah, peut-être. Ok.
Tu peux juste échanger de
Oui,
ça suffit.
Alright. So now I state the formula, and it says the following thing. That, so, so we take this quantity, and we divide it by q to the following power, dimension of bungee. And I can tell you what that integer is. So, parenthetically, the dimension of bungee is g minus 1 times the dimension of the group, where g is the genus of the curve. And so, here is the formula. So it's the product, it's an infinite product over places of your curve. The following things. Here, you'll take q to the power qx to the power the dimension of g. Qx is the number of elements in the residue field of x. I'll write it. So qx is fx, and fx is the residue field.
Of the curve.
Residue field at that point. We fix the place. And here I take the number of elements of G. Okay, so you see here Q was in the denominator, here's in the numerator. I don't like that. We'll invert. So let me rewrite this as follows. Instead of talking about G, I'll talk about BG, the classifying stack. And I'll rewrite the right-hand side as follows. Same product. I'll write in the denominator to the dimension of BG. Dimension of BG is negative the dimension of G. And here I write BG, which is now an algebraic stack. Count the number of points in that sense, which is exactly 1 over the number of points of G. Alright, and now you see the two things look kind of the same. So here we're counting the number of points in bungee, and it becomes a product. So by the way, there's also a convergence problem, because it's an infinite product, so it converges. It's an Eulerian product, and well, elementary argument shows that it converges. So what you kind of deduce from this is that some idea, which is of course not at all true, is that bungee is, in very emphasized quotation marks, the product of these BGs. It's in no sense true, but somehow it's true at the level of counting. The kind of number of points becomes the same. So this is the idea that we want to realize. So it's kind of local to global principle here that it manifests itself in the counting. Okay. So we'll attack this Tamagawa number formula by geometry, so we'll use the Frobenius. So let me remind you some very general thing. So let's again YB first an algebraic stack which is quasi-compact. So in this case, there's a classical formula, it's a trace of the Frobenius, Grothendieck-Leptis formula, of the compactly supported cohomology of Y. So a priori, this is an L-adic number, and this is a rational number, so it's an equality of L-adic numbers. So compactly supported cohomology makes sense for algebraic stacks. So,
Even non-quasi-compact ones?
well, this is for quasi-compact. So I want to apply it in the case of Bun-G, and there is little something to prove. That in fact, this equality stays true for Bun-G, so that this non-quasi-compactness of Bun-G can be controlled. And indeed, it can be controlled. It's based in classical reduction theory.
And here there is some convergence again.
Yeah, well, so far not. This is quasi-compact. For Bun-G, there is a convergence problem.
No, but the cohomology, the compact cohomology, the dual, for smoothing a dual
Right.
of cohomologies are an infinite number because of stabilizers.
Yeah, but in this, but you always get, in this case, for quasi-compact geometric series.
Yeah, I know this from, yes, that
Yeah.
people observe that this converges formally.
Yeah, but I mean, kind of, there's a convergence problem, but it's kind of automatically solved because you're dealing with a geometric series all the time.
Okay.
So the formula stays true for Bun-G. And it's reduction theory.
This cohomology is compatible with inductive limit of these parts which are finite type, yeah?
Yes.
Okay.
Yes. Okay, I want to massage this form a little bit. So I'll tautologically rewrite this as the trace of the inverse of the Frobenius on the dual vector space to that, and the dual vector space will be what's called the Borel-Moore homology. It's cohomology, but with coefficients in the dualizing sheaf. And so now, let us suppose that this Y is smooth, as is our Bun-G. In this case, the dualizing is, well, it's a shift in the Tate twist of the constant. So we can rewrite it even further, and we'll rewrite this as trace of the Frobenius inverse on just the usual cohomology, but divided by Q to the dimension of Y. And now you can see why I wrote this. Well, because it's exactly the kind of quantity that appears on both sides. So, wants to express the following idea. What? Okay. Yeah. And again, in big quotation marks, I want to express the idea that the cohomology of Bun-G, it's a well-defined graded vector space, is, again, in emphasized quotation marks, the product over all places of the cohomologies of BG. Again, it's not at all the restricted product in the sense of Adels, this tensor product, it's not that. So, and this is what I want to assign the meaning to. So what do I mean by taking this product? So that,
PG index X, I suppose.
Vector X.
well, my G is constant, but indeed,
Okay.
what I think of when you look at a non-constant is BGX, of course.
It seems like maps from its curves to BG, like continuous maps, yeah.
This is an algebraic geometry, right? So far.
No, but you have access which are close points, but now you're doing cohomologies over the FQ
Exactly.
bar, so,
So, okay.
it doesn't make
It doesn't make sense, indeed. So, again, take it very, very holistically. I will now assign sense to it. So I will make sense of the right-hand side in such a way that when I take the trace of the Frobenius, I actually arrive to the product formula as written. So that's what I will do. What is the
Just
erasure policy?
Just shift the two ones. Don't use the third one. It's easier. Just shift the number 2 and 3.
You think?
No?
Yeah.
Shift.
I trust your experience with this. Yeah.
Just as its formula looks very similar to this is Gelfand-Fuchs cohomology. Consider smooth manifold. It's for people of different properties, infinity manifold.
Yeah.
Consider Lie algebra of vector fields. It has some cohomology, and it has kind of formal vector fields with some truncation of some nice homotopy type. Consider space of sections, the rational homotopy type of the space of sections.
It's not an analogy. I mean, you can derive this from that.
Yeah, it's kind of.
The only problem is that, and it's actually legal derivation. I will not use it, but I'll use another derivation. What you're saying is just it's completely legit.
Yeah.
You can actually do it this way. So parenthetically, in number theory, we don't really like Lie algebras, so that's why I won't do it this way.
Yeah, but it's also something called like Siegel, whatever, something here. This
IT bot.
IT bot, whatever.
Oh, so that product formula is,
In a sense,
well,
yeah.
I haven't defined it, I haven't defined the right-hand side.
Yeah.
Once I do, it will be the IT bot formula, which of course I will say very explicitly, but in 20 minutes maybe. Okay, so now we'll switch to a very different type of mathematics. We'll be doing some adjoint functors, okay? So, here is my x, and here is the projection to the point. I call it px. And we'll be considering the category of derived category of analytic sheaves on x. And I'll just write to you what it means that two functors are adjoint. So here it will be sheaves on the point. Well, same as that, well, complexes of analytic vector spaces. And there are two adjoint functors that connect these two categories. This is the cohomology with compact supports, and this is this upper sheet functor. Yeah? Adjoint. So what does it mean they're adjoint? It means the following: that home in the category of vector spaces from some object f to v is the same thing as home in the category of sheaves from f to px upper sheet of v. Okay. So now I want to change my problem. Instead of talking just about sheaves, I'll talk about sheaves of commutative algebras. Well, what do you mean commutative algebras with respect to what kind of product? Tensor product. But what kind of tensor product? So what is tensor product? Tensor product is, you have f and g, you take f and g, and you pull back. That's your tensor product. However, I want to pull back with a shriek. I like shrieks better than stars, for a good reason. So this is my tensor product.
Inner tensor product.
Pardon?
Inner tensor product. Compared to the
Well, this is the external tensor product, but there are two inner products. There is star and shriek. I want a shriek. And I might omit writing this shriek all the time, but this is always the one I mean. Okay. And one can talk about commutative algebras. Inside sheaves on X. And, well,
So here, of course, sheaves is a derived category, but I wonder about finiteness conditions because in your previous talks you had unbounded things and so on. And here, in analytic context, people usually consider only constructible and bounded.
Correct.
So what are you doing exactly?
so I can tell you exactly what we do. We take the usual elliptic sheaves and incomplete. So that's the formal definition.
Incomplete of the DVC.
Yes, the DVC, yes. DVC bounded constructible category. So this upper shriek defines a functor like this. So here are your forgetful functors that I call oblivion. You forget down the algebra structure.
So the point is you're defining what it means to be an algebra, commutative algebra, using this tensor product.
Yes, I mean commutative algebras. So this tensor product defines what's called the symmetric monoidal.
Right.
Or I can't see over here.
Yeah.
Symmetric monoidal structure of the category, and then it makes sense to talk about commutative algebras.
Ah, so you don't speak about commutative algebras in high sense?
Of course I do.
Ah, yeah.
Yeah, of course I do that.
To do what?
No, it's
Commutative algebras,
it's
of
not
course.
In plain direct, not in plain direct
Yeah.
it's probably but kind of enhanced by spectra and
No, you don't need spectra. No, you don't need spectra. It's just infinity category.
infinity category.
Yeah, it's infinity category.
So define what it means to be commutative, basically,
Well, just to set up.
and all the associative laws and all that stuff.
Yeah.
Yeah, you have to specify this infinite tail of commutativity and associativity relations, and you have to disengage yourself from triangulated categories and do it in the proper higher categorical context. So this upper sheet just induces an upper sheet functor of commutative algebras. But what about this lower sheet? Well, I have this beautiful diagram here, so let me write one down underneath it. Well, you have these functors. You can take all of their left adjoints, and the diagram will still commute. So it will be com-alg. I'm not even labeling these arrows yet. Well, at least I'm not labeling those, but... So this is the left adjoint of what we had before. This is px lower sheik. And this is the functor that actually I'm interested in. That's the what we'll be talking about. And I have a name for it. I have not a name, I have a fancy symbol for it. Integral. Okay, just for fun, do you guys know what these arrows are? What is the left adjoint to the functor of forgetting forgetting the structure of commutative algebra?
To be free.
Free. If you have a sheet, you can create a free algebra.
Always commutative.
Pardon me? Commutative. We're in the commutative world. So this diagram commutes.
Excuse me, my stupid question. Is there a unit in this?
A very good question. And I'm... For now, yes. But we'll soon get rid of the unit.
Oh, no.
For a good reason also. But right on. Okay, so this diagram commutes, but let me be very naive. Let me ask, would this diagram commute? So I'm asking the following question. Start with an algebra, and I want to compute the value of the left adjoint. Is it true that, and I want to compute this left adjoint and just look at the vector space that I get. Is it true that this vector space is very naively, forget down the algebra structure and take the comodular Quebec support? What do you guys think? Yes or no?
Could you repeat that? That was too fast.
Yeah, I'm saying, well, the diagram with free commuted for tautological reasons, because you just take left adjoints of everything. But would the following be true? Will this diagram commute? I.e., I want to compute what this left adjoint looks like. Start with the commutative sheaf of commutative algebras, calculate this mysterious left adjoint, and then just forget the algebra structure. Will it be the same, but forget down the algebra structure and compute the left adjoint?
Surely not.
Surely not. There's no reason, and it's completely false. So I would like to compute this. I will be interested in this functor. And the reason I'm interested in it is because to make sense of this fancy product. Okay, but before I try to define it, let's do a very simple case when X is a finite set, not a curve, just a really finite set. So let's solve it in this case. So X is a finite set. So what does it mean to be a sheaf commutative algebras? All it means is that you have a commutative algebra for each point. Okay. So I'm interested, let's call it B, this commutative algebra. So I'm trying to calculate this mysterious integral into an algebra that I call, what do they call it? A.
It's an ordinary algebra.
Yeah, I'm talking about this fancy higher category, but this commutative algebra, but the problem this problem makes sense for just usual commutative algebras in degree 0.
Yeah, but
we're talking about like very elementary stuff.
Yeah.
So I'm interested in this mysterious object, which is supposed to be home of commutative algebras. Well, sheaves on X. Remember, sheaves on X is just commutative algebra each point from B. Well, call it Px up a shriek, but what I do, I just take this A and kind of put it on X, just put a constant algebra in each. And by definition, this right-hand side is product over X, home of com alg, from what I had at each point to this A. So, again, right-hand side for each, so you have this bunch of commutative algebras, for each of them you specify a homomorphism of A, and I'm looking for a commutative algebra such that
That's a problem.
you guys are good. Okay, I'm very glad that people are awake. All right, and now we going back to Luke's question. Take the unit out. What do you get then? Now my algebras are non-unital. This still makes sense. Who is this guy? X is a finite set. Let's take the simplest case. 2. 1 and 2. So I have B1 and B2.
Without unit, yeah.
No unit. Who is this guy?
B1 plus B2 plus B1 plus times B2.
You guys are good.
Yeah. Add unit multiplying to remove unit, yeah.
put the unit and you remove. Exactly.
Well, it's very satisfying to be in this audience. Indeed, a non-unital algebra is the same as an augmented unital algebra. And so you know what to do. Put the unit in, take this as a product, take the unit out. That's what you get. Perfect. Okay, if you're so good, give me the answer for general finite X.
Sum of all non-empty finite subsets.
Perfect. Okay. Okay, but that
The sum of the partial product over all subset of X.
perfect. Okay, but that merits a special symbol. Indeed, for a finite set, it's the direct sum. Let me call them I, all finite non-empty subsets, and for each, I'll take the tensor product over all those x's. Dx. Okay. So now, how do we want to generalize it when X is no longer a finite set? Well, it must incarnate this kind of idea, right? After all, because if we have this finite set, something like that must appear in general. And how am I doing on time? Pardon?
32 minutes. Still 32 minutes.
Okay. So now X will be a curve, but in general, what I'll say now to define this integral, X will be arbitrary connected scheme. But connected is important, unlike the finite set, because it's connected. And to this X, we'll assign another geometric object. It's called the Ron space of X. Ron is last name of Zivlan. It's a guy in California. So, it's a geometric object.
Zifron?
Yeah,
Yes.
it's your student,
Ah,
yeah.
my student.
Okay, good. Well, how do we define objects in geometry? As Grothendieck taught us, define the function of points. From an affine scheme S to Ron of X would be the set of all finite, non-empty subsets in home from S of X, S to X. It looks pretty horrible. So you can ask, is it representable by, see, no multiplicities here, really subsets. You can ask, is it representable by a scheme, and what do you guys think?
No.
Yeah, it's like, if it was a scheme, what would be the dimension? It's like not a scheme, so what is it? It's nothing. It's what we call the pre-stack. So by definition, a pre-stack is an arbitrary functor from, let's say, affine schemes of. Well, you can say to sets, but I want more general, because I want also to incorporate Bun-G to groupoids, of which sets are a particular set, a particular case.
I think that in some places a pre-stack has to satisfy a part of the restriction, not...
Here, none.
Ah, okay.
Just completely general. Okay, why do I want this guy? Well, because it already appeared for finite sets. And if it already appears for finite sets, I want to have it in general. And moreover, I want to have sheaves on it. So how do we make sense of sheaves on such a gadget?
Of course, it is a functor in the weaker sense of pseudo-functor or whatever,
Yeah.
because otherwise it's...
What do you mean pseudo-functor?
That is, you are not working in the strict sense of strict functors. Yeah.
Yeah, I guess for me, strict functors don't even exist. Yeah, I mean, it's the functor in a reasonable sense. All right. So let's talk a little bit about sheaves. Let's first talk about sheaves on schemes. So what are sheaves? Well, for me, sheaves is a functor let me, for a little bit, not specify what kind of categories I consider. You can consider for now triangulated, but we'll see exactly what I have to pass to the higher world. Okay. Opposite, so i.e. to scheme S, you assign this category of sheaves, but for morphism, you assign like sheaves. The sheepfold function. Okay. So now I give myself a pre-stack Y. So what is sheaves in Y?
So here sheaves are what kind of sheaves?
Yeah.
In the sense of int completing and
Yes.
so on.
Yeah. This makes sense without, I could do it before int completion, but let me do it after int completion.
In categories, is it by chance the higher ones?
That's exact. I'm leaving it ambiguous for the next 2 minutes. So you can say, you can do it either triangulated or higher, but in a few minutes I'll explain why I have to stick to higher. Not in a few minutes, in 1 minute.
I'm sorry, that's an F over shriek there?
That's a shriek, upper shriek. Okay, what's sheaves on Y? Naively, what's a sheaf on Y? Well, you test it by a fine scheme. To specify a sheaf on Y, you just have to specify all of its pullbacks. Naively. So this is for every affine scheme and a map little y from S to Y, i.e. an element little y in home from S to Y, you specify plus compatibility conditions, namely if you have a datum of commutativity of this triangle, because Y is a groupoid, it's not that they're equal, it's specified an isomorphism. To each such, you specify a compatibility. F a sheik from what you had on S2 with what you with what you have on S1. And compatibility for twofold compositions. For S1 to S2 to S3. But such a thing has a name. So this to say for each blah blah blah, there's a word for it. In other words, what they're saying is that sheaves of Y is the limit over what we call affine schemes over Y opposite of the puncture shv.
And if you define using, instead of F upper shrik, just F upper star, you must get something equivalent, isn't it? Because you have a smooth atlas, smooth...
No, nothing is smooth. Y was completely arbitrary.
Arbitrary stack?
Pre-stack.
Pre-stack.
Yeah.
Ah,
You get a different theory, they are related, but it's different gadget.
So why is an object like that?
Pardon me?
Why is an object like that?
Why is an orbit? Luckily, we still have it.
But no, so for an algebraic stack, without the infiniteness condition, just locally...
For algebraic stack with smooth atlas,
yes?
you will get an equivalent definition.
Okay, this is what I
Yeah.
thought. Okay.
But for something like the round space, you will not get an equivalent definition. Not at all, actually. All right. But now comes the moment to explain why I actually need higher categories, because, well, it's a well-known fact. It's a very bad idea to take the limit in triangular categories. So it's ill-behaved. You will not be able to compute anything. So for that reason, we...
So could you use, what do they call them, derivators instead?
What?
Derivators?
I don't know what
No,
Derivateur, so it's one of
some intermediate machine which was studied in Paris here.
my understanding is derivators are sort of like derived categories. They allow you to do limits, but they don't have all the stuff of higher.
So I don't know, because I don't know what these are.
They're really very nice.
Yeah.
It's one of the lessons Grothendieck sort of did, I think.
Yeah, there are several series about
Yeah,
derivatives.
this is Max Groth, who's
So I don't know. So I know that for...
Yeah, no, but is this larger series kind of more general model?
I know,
Yeah, but
I know.
yeah, it's
I
less
find it easier
explicit.
to
Yeah,
understand.
it's less explicit here, but okay.
So we've got this. Now let me just introduce a couple of more pieces of notation of what you can do with this. Kind of by definition, if you have a map between pre-stacks, by which we mean a natural transformation between these functors, it's built into the machine that you have an upper sheet functor. Pullback. You can ask, does this upper sheet functor admit a left adjoint? Well, if you're working with elliptic sheaves, from the way the theory is set up, it does always admit a left adjoint.
This is a map of arbitrary...
Arbitrary pre-stacks.
So on the pre-stack, but still you're working with the category of affine schemes, that is a finite type, or?
Yes,
Okay.
yes, yeah. When I write affine schemes, I meant a finite type.
Ah. A finite type
Over your ground fields.
uh-huh.
In this case, it's a cube. Happens to be always the case. And just as a matter of notation, let me introduce this. So let me go back to the projection to the point, call it Py. Instead of writing Py lower sheet, I'll write cohomology with compact supports. That's notation. And when I pull back from the point my QL, I'll just denote it by the dualizing notation. But now let's combine these two pieces of notation, and let's take the cohomology of compact supports of the dualizing. Do you guys have a name for it?
Verdi.
Hmm?
Verdi from
No, it has a name.
Reinbourg.
No. It starts with H. It's called homology.
Yeah.
Compact supports cohomology of the dualizing is homology.
Okay.
But now I will not, if I don't like the letter H, I'll write letter C.
For cohomology.
I want to call it cochains because we are really in the
chains.
Change.
chains. I put the lower star. We are in the higher world, so we're not taking individual cohomologies, but it's really kind of chains. All right. Now go
I'm sorry, F lower shrink is between Y1 and Y2 or between the chief category two? Upper shrink. Yes. Yeah, yes. Okay. Because it's compatible with what you wrote before.
Thank you. All right.
So this left adjoint just exists by abstract limit kind of argument?
No, it follows formally from the fact that lower shriek exists for affine schemes.
Ah,
Just from there.
I see.
From there, it's formal. All right. So,
So
why am I
that's
talking
really,
about?
really some geometry then. That's not,
Well, yeah. You use the entire theory of elliptic sheets. Just note that in this theory, we don't have upper stars and lower stars. We have just the shrieks. If you want lower star, you have to say pay extra. So why am I talking about this? Well, because we want the run space.
We are quite far from Tamagawa Number.
We'll start going back. So we're at the highest point of the trajectory now. We start. All right. So we start with B, which is a commutative algebra in sheaves. And if you remember what we did with finite sets, we actually, from B, we produced another object. Let me call it factor B, which was actually a sheaf.
So these algebras are no longer unital?
They don't need to be unital. In our case, they happen to be unital, but they don't need to be. And I'll get, this unitality, non-unitality is the core of our work with Jacob. And I'll get to that discussion at the very end. So let's hold on with this. But I mean, it's unital, but you're forgetting the fact that it's unital. And we do it by the same procedure as in the case of finite sets, namely the fiber, the sheet fiber of factor B at, let's say, just field valued points of the run space corresponding to just an n tuple of points over the initial space X is the tensor product I of the Schlick fibers of your initial B at these points, like we did in the finite set. Remember, it was bx1 times bx2
Unital case,
in the non-unital case.
non-unital case.
Yeah.
That's
Again.
because you're taking Ron, yeah.
Yeah. It might have a unit, just forget it. Okay, and now, so
So if it has a unit, the Schlick fibers have unit also?
they do.
Ah, okay.
Finally, so the answer for this integral happens to be cohomology with compact supports over the Ron space of this vector B. So call it lambda. So I went to the older discussion to define, to construct this left adjoint. And here's what I'm saying. And it's really kind of fancy, right? You have to go to the squeeze stacks and all this stuff, and you can't do it otherwise. It's really kind of, you have no choice. You must do it. If you want explicit formula, you construct the Ron space. From your B, construct this sheaf on the Ron space, vector B, and then take its cohomology.
You say homology or cohomology?
It's cohomology with compact supports. It's the only thing that exists in our formalism.
No, because you wrote homology at all.
Ah, homology is cohomology with compact supports of the dualizing specifically.
So you have actually, you need enough machinery to actually prove that it makes sense. Otherwise, if
Pardon?
you need enough machinery, because all of those things are with higher
Yes.
things, so you need some nice machinery that allows you not to start
And we do
verifying.
have it, so we have the machinery now.
Okay.
So Lurie's higher algebra is that machinery.
Okay.
All right. So now let's go back to Tamagawa. So one step closer to Tamagawa. So let me just say that now a certain symbol will appear on the blackboard which hasn't been introduced. I wonder if you'll catch it. I'll take a very particular B. So and I take a very particular C. And I claim, and both are sheaves of commutative algebras on the curve, and I claim that I have a map from B to C.
C lower star?
You got it. I haven't introduced, I've only introduced homology. I haven't introduced cohomology. What is that?
I was waiting for that also.
All right. So I claim that homology of anything is naturally coalgebra, therefore its dual is an algebra.
But what in which sense the dual?
Linear.
No, but
We are in vect, take the linear dual.
no, but the vector, according to what you said, includes direct
Yeah.
units.
So it's a symmetric monoidal category. In there it makes, there's operation of duality. There's operation of duality, it makes sense.
No, but you said that sometimes you take the int completion. So you take...
Yeah. It's infinite dimensional.
Okay, but the dual of an infinite dimensional guy is an inverse limit of the dual of the finite dimensional pieces. So
But it's fine.
and so
The dual of a coalgebra is nonetheless an algebra.
Yes, but not the converse.
Not the converse.
the dual of a coil, of course, it's an algebra just with a huge uncountable. Okay, if you
Perfect.
don't-
However, it just so happens that each of these have finitely many, is finite dimensional, each cohomological degree. So so this duality is not as horrible as it would be in general.
So each cohomological degree is finite.
Yeah, but I don't care. I mean, to formally give the definition, it makes sense. It's huge, but it's okay. All right, now I claim there's a map from B to C. So let's say there in Ely, where it comes from, as algebras. It means that for every point of the curve, I have a map from the cohomology of BG to the cohomology of BunG. Where does it come from? Depend. So for each point of the curve, I can map cochains on BG to cochains on BunG.
Evaluation map.
Evaluation map. So you have a map from X times BunG to BG. So for each point of the curve, you have a map from BunG to BG. You have pullback and cohomology. So therefore, a junction. From here, we obtain a map from the
So that's where this product of all the BGs come from. This is the formula.
Yeah, I should have said maybe, sorry. When I start with the Shiva cumulative algebras, the definition of what I mean by this is that. So, that symbol that made no sense by definition means that.
But maybe we should also mention that was in rational homotopy theory, and it was developed how to calculate homotopy type of space of maps from some C double complex of small dimension to high connected space. Yeah, and essentially what you do.
Except in algebraic geometry.
Yes, yes.
Of course, this is what we do.
Yeah, that's.
But in algebraic geometry, it doesn't work except when X is a curve and the target is BG.
Ah, yeah, because it's stuck with 4 dimensions. Yeah.
It's infinitely, it always works. But
No. Dimension should
Yeah,
be
yeah.
less and it's
right, correct. But in algebraic geometry, you have.
Dimension 2 of curve.
Yeah.
Dimension 4.
But if you start with the surface, there's nothing.
Yes, it will not converge. Yeah.
So, a junction. So you get the map from here. And now I state the real theorem. By the way, this map makes sense when X is an arbitrary algebraic variety, G is an arbitrary group whatsoever. And now X is a curve, and G is simply connected. Then,
And semi-simple,
sorry, semi-simple simply connected, otherwise not.
it doesn't make sense.
Then the map is an isomorphism. And so, and this theory has a name. This is the Etienne-Bott formula. Of course, they didn't write it like this because at the time there was no run space or anything like that. However, the left-hand side, although it looks very fancy, it can be computed very explicitly, and when you compute it very explicitly, in terms of the cohomology of BG.
So is this the paper in
Yes, it's that
83, but they work over C?
Yes, they proved it over complex numbers, and they proved it by the method that Maxime is talking about. It was they gave it differential geometric proof. So
It's analysis, okay.
yes, it was analytic proof, basically along the lines as Maxime is explaining. But the statement, if you write it in this form, it makes sense in general, and it holds an arbitrary ground here. It holds algebra geometrically. So this is the kind of the real assertion, and as a corollary, so once you have that, you can from it you can formulate takes. Well, you need some work, but numerical product formula. So if you take the trace of the Frobenius on both sides, you actually arrive to the product formula that I wrote before. That's the product of traces of inverse Frobenius is on the cohomologies of these things will be the trace of the inverse Frobenius on the cohomology of on this. Okay, and so the real work is here. So the question is, how much time do I have? 5 minutes? 5 minutes.
So, and why you get exactly the product instead of those finite, before we said that we get something, we had the product over finite sets, subsets of sets.
Yeah, but you can see the product of things which is 1 plus something.
Yes.
If you have infinite product, you can write it sum of infinite or finite subsets. Take infinite product of 1 plus some numbers.
Yes, but this means it is 1 plus something and the 1 is out. But here the
No,
one
one is, yeah, it will be
the
There's a little bit of work required here. I'm not saying it's immediately evident.
but you are still taking things which are a unit or not. The C upper star VG as a unit.
Yes, so the way we deduce it is as follows. So we actually rewrite it, the left-hand side, the way that Etienne and Bott rewrote it. It's a symmetric algebra on something, and we calculate and see. I can.
Okay.
So maybe, if you want, in question time, I can write the Etienne and Bott formula, say what that thing is explicitly, and from there show how to deduce this.
Okay.
So in the remaining now 3 minutes, I can try to say how we prove this. So it also, well, it requires proof. It's not like. So if you wish, this is a local to global principle. We're saying that. So the left-hand side is essentially local. We assemble from finite subsets of the curve. And the right-hand side is global. It really has to do with the kind of automorphic objects, Bungie. So something needs to be done. And so it doesn't come for free. So let me say what the key geometric ingredient is. We introduced this gadget called the Fine-Grassmannian. But it's the wrong version. Again, I don't have time now. I'll be happy to add more details in question time. So it's the moduli space of a bundle equipped with a rational trivialization. And there is this map that forgets the rational trivialization. And it also projects the Riemann space, which says that, away from which sets you have the rational trivialization. So the key geometric result is that the homology, so this map is homology, is a homology equivalence. So this map is locally a product. So basically every bundle admits a rational trivialization. What it says is that for a given bundle, the space of rational trivializations is homologically trivial. That is to say that the space of rational functions from a curve, which is a horrible, but manageable pre-stack, imagine, we're really talking about the space of rational functions. You can make sense of it as a pre-stack. Rational maps from the curve to the G, to the group G. You can make sense of it. You can actually calculate its homology and prove that it's trivial. It's what we call homologically contractible.
But is it contractible?
It is.
Yeah, not just
Yeah.
no. Yeah.
It's actually, yeah. And
But the space of maps from a point to G is not contractible.
not at all.
But rational maps is no point.
Yeah.
But rational map includes constants maps.
Including.
But that's okay.
Yeah, you've got more room.
Yeah. So I can tell you the reason. I mean, again, I'll be happy to comment how that comes about. And this is specific to dimension 1. So none of that would be true if it was either lower dimension, as you say, point, or the surface. It's really kind of the thing of.
So what is the definition of the Ram-Grassmannian over a base S? It's bundles on S cross X.
I'll say that in a second. So maybe I think I have to officially finish because it's 11:05, and then I'll answer this and everything else. Shall we do that?
Oui.
Yeah. Oh, thank you.
Okay, so we will take a few questions. So maybe we start as usual, Tokyo, then Beijing, and then Paris. Okay, so Tokyo, do you have some questions?
Any questions? なんかありますか
Yeah, it's similar to nobody has a question in
Okay.
Tokyo. Sorry.
Then Beijing, do you have some questions?
等下我问题吗？你直接说就行。Just go ahead.
Go ahead. Oh yeah, so it's a question. So it says a paper by Franco and Go where they propose a geometric version of the trace formula, and the Artier-Bott formula yes, occurs at the spectral side of the trace formula. So do you see there's a possible connection between this proof of Tamagawa number and the proposal of geometric trace formula?
Good question. The answer is I don't know. I haven't studied that paper in sufficient detail. I should do it. Just thanks for the suggestion.
Yeah, because in the number field case, Tamagawa number conjecture, of course, is proof as a consequence of the trace formula consideration. So it seems that there should be a connection. And, maybe in the formula field case, the trace formula, as they say, is interpreted as a consequence of the Artier-Bott fixed formula, the Grothendieck that's a trace formula.
Okay, I'll go and look. I haven't, so I'll do it.
Other questions from Beijing?
Can you say a word on the proof of the left-hand trace formula for Banji?
Yeah, I mean, so how do I deal with these infinities? I mean, right, with convergence.
Yeah. Yeah.
So it's a reduction theory. So let's deal with SL2, okay, just for as an example. So how does Banji for SL2 look like? Well, it looks as follows. You can take an open piece, which are bundles which are not very unstable. Yeah. You take bundles which are not very unstable. Well, in general, Banji is stratified by the degree of instability. There are semi-stable bundles, and then for each integer n, there are bundles that look as follows. So they are extensions of like this, where L has degree specifically n is a positive integer. And so this looks very, very simple. It's, well, it's a stack of extensions of this by this. And, well, you explicitly see, and then you sum up over all integers n, and you get geometric series. So on each stratum, so basically what happens is Banji looks as a finite union of geometric series. And that's how you control it. So in other words, you prove for stacks of for algebraic stacks of finite type, and in this case, this guy, it's not a finite type, but it's again a finite union of things that look something like finite type times something that looks like a geometric series. When I say geometric series, I mean it's 1 over an point over an. Well, this is a fine translation group, and when you count points, you literally get geometric series.
You made the classifying space of an.
Yeah,
Yeah.
that's vector space. So these, as you vary,
Yeah.
vary the degree.
Okay, other questions from Eugene?
No more questions.
Okay, thank you. So, questions in terms?
Concerning this
Run space?
run space. So first of all, there is a result that I think I heard in some seminar, but I don't remember exactly. So the fact that the bundles are rationally trivial, but also over a base, that is locally for the Tal topology, they are rationally trivial on the total space, yes?
Right.
There is some result like this.
Drinfeld-Simpson.
Who?
Drinfeld-Simpson.
Drinfeld-Simpson?
Yeah.
And now, the rationally trivial in this context means trivial outside the scheme which is finite over the base, or
So in this case, so when the group is simply connected, it's much, much stronger than that. It says that if you take any non-empty divisor,
Yes.
On the,
pardon? On the curve,
on the,
on the curve, then after an étal base change of your scheme of parameters, it becomes trivial outside of the divisor.
Ah, okay.
For simply connected, for semi-simple, it means it's, for semi-simple, this is true.
For semi-simple bundles. Okay, for constant groups, you mean?
Okay. So this is proved for constant groups. For group schemes, it's proved only in our paper with Jacob, and it's proved in the simply connected case.
And again, outside the given.
Yes, you specify a section, and after a tal base change of the scheme of parameters, the thing trivialized outside the given
Okay.
section.
So now concerning the definition of Grassmannian run,
Yes.
can you say what it
Yes,
is?
absolutely. So first of all, I said that it maps to here and to here. So I better, if I want to S point of this, I have to specify point of here and point of here.
Yes.
So home from S to Grassmannian 1 is the following. First of all, it's a PG, it's a G bundle on S times X. It's a point, S point of Bungie. Also, it's a finite subset in home from S times X. And now I specify my crucial Grassmannian type datum. I specify a trivialization, P0G is a trivial bundle, on X times X without, when I remove a certain divisor. Which divisor? I take the union of the graphs.
Okay.
So I runs through this finite set I. For each element, I take the map from S to X. I take this graph, throw it out.
Okay, so this roughly explains this, and then there is another vague question, but because excuse me for this, but still, the what concerning this integral of those px upper roof, upper shriek of C star BG on the, so we work there with tensor product of thing whichever you need, but yeah, so I want to understand roughly why it is like what Kontsevich stated about the product of one plus alpha I is one plus finite product.
It's a great question. So, no, first of all, literally, when you take the finite set, you get exactly that. If X is a finite set,
Yes.
then the way this integral is defined, remember integral was cohomology with compact support of what I call factor F.
That is the cohomology of the guy which is
So I wonder if we should
maybe take another question. Then.
should I answer or first question or should I?
Yeah, you should.
Okay, so again, integral is by definition cohomology with compact supports on the one. So if X is a finite set,
yes.
you literally get what Maxime said. Because factor B, what is it? So let's say, suppose X is a finite it's a two-element set.
Yes.
What's factor B? Well, around, in this case, is disjoint union of 3 elements. It's 1, 2, and 1, 2.
Yes.
And what's factor B? So you get B1, B2, B1 tensor B2,
Yes.
and cohomology with contact supports is just direct sum.
Ah, okay, so you get the,
It's like 1 plus B1 times 1 plus
okay,
B2.
and then how this is the product for,
1 plus B1 times 1 plus B2.
how this is the product for.
So you're asking, why do I call this quotation product, tensor product in quotation marks?
So then you want to get something which is the numerical product formula, which was actually a product formula.
Okay, so maybe we should terminate an LM for this.
Okay, except if you can say just in a few words. It will take time.
Pardon?
You cannot answer just in a few words.
Yeah, it's,
Okay, so maybe we take another question. There is no other questions. Okay, then we will say goodbye, since it should be now 7 p.m. in Tokyo.
we need to,
Yeah, exactly, we need to go to so. Okay, so goodbye and see you in 1 month.
Bye.
bye-bye.
Bye bye.
Bye.